Hello everyone, my name is Nidhi and I'm a Associate Professor in Gyan School of Pharmacy. That is a part of your Suresh in Jaipur. And today we are going to discuss the topic that is the fats and oil that comes in your pharmaceutical organic chemistry second in your B Pharmacy third semester. Third second year. So here we are going to study about the fat and oils and what are the reactions that are happening in these fatty acids. And also we are going to learn about this hydrogenation, rendicity, drying oil, and the student outcome. They will going to know about the fats and oil, and they will also going to know about what are the reactions of fatty acids, hydrogenation, hydrolysis, rendicities, drying. So these all we are going to study here. So let's start our topic. That is that in the previous lecture, I have already told you about the what are the fats and oils, and today we are going to discuss this fatty acids reaction. In the last lecture, we have discussed for the comparison between the fats and oil, how they are made, how the fats are made from the saturated hydrocarbon, and the oils are prepared from the unsaturated unsaturated compounds, and the fats are the solid at room temperature at 25 degrees centigrade, and your oils are liquid at room temperature, so they need less melting point, so their melting point is less low and as compared to the fatty acid, because fatty acid is solid at room temperature and they need more temperature, more melting, and the melting point is more as compared to your oil. So today, this fatty acid reaction, we are going to discuss about this fatty acid reaction. So this is your Fischer esterification. This reaction is known as your Fischer esterification. So this is the Fischer esterification. Is the esterification of a carboxylic acid by heating it with an alcohol in the presence of a strong acid as a catalyst. So here in the Fischer esterification, this is a esterification reaction and is named after this Fischer. And in this, you already know that the fatty acids are prepared from the your triglycerols are reacting or the reacting with this your fatty acids, and then there is a glycerol is reacting with this triglycerides, and then there is a formation of the fats. So here also in the esterification reaction, there is a reaction between this carboxylic acid and the alcohol, and there is a formation of the ester. That is why the reaction is named as esterification. So here, this Fischer esterification is the esterification of a carboxylic acid by heating it with an alcohol in the presence of a strong acid as the catalyst. This is the reaction type. So in this reaction, nucleophilic acyl substitution, you will see here this RCOOH plus ROH. This RCOOH is your carboxylic acid because it has a functional group COOH plus ROH. ROH is your alcohol because it is having this functional group OH. And then in this acidification, we are heating it in the presence of this acid catalyst, that is your H positive, and there is a formation of this ester, that is your RCOOR. So here, and the water molecule is removed out from here. So here you will see that this carboxylic acid is reacting with this. So here this H is removed here from here, and this R is attached to this O, and this R and OH forms here water molecule. That is why water molecule is removed out from here, and there is a formation of this ester. So this is a type of a nucleophilic acyl substitution. Here in the acyl, there is a substitution happening with the nucleophile. So here you will see that this acyl is the compounds that are having the COO group. So this is their acyl. This is reacting with this, and there is a formation of this. Next, in the step first, you will see here that an acid-base reaction, protonation of the carbonyl make it more electrophilic. Means here, this is an acid-base reaction, and protonation of the carbonyl make it more electrophilic. Means here protonation is happening. The addition of this H positive. This H positive is adding to this carboxylic acid O. You know that this oxygen will withdraw electron from this carbon atom. So here there is a partial negative charge on this oxygen atom and partial positive charge on this carbon atom. So here you will see a proton. This H positive will add to this negative portion and there is a formation of a bond. So here this is known as protonation. When there is addition of this H positive, that is your proton, then this reaction or this phenomena is known as your protonation. So in this, the protonation of the carboxylic carbonyl make it more electrophilic. So here, due to the addition of this H positive on this oxygen atom, this carbon will become more electrophilic, or this carbonyl may become more electrophilic. So here you will see H positive this oxygen is having a lone pair. That is why it is attached to this. Now it is having a positive charge. Now it is having a positive charge and one lone pair. So here this this ROH, that is a CH3, CH2OH, ethyl alcohol will react to this carbon atom. So here you will see this will react to this carbon atom and there is a formation of this bond. So in the step 2, you will see the alcohol O function as a nucleophile. Here this O will function as a nucleophile and attack the electrophilic C in the C double bond O with the electron moving towards the oxenium ion, creating the tetrahedral intermediate. So here alcohol O functions as an nucleophile. So then in alcohol O is functioning as a nucleophile and attacking this electrophilic carbon in the C double O, and the electrons are moving towards the oxenium ion. So here the electrons are moved. See, the electrons are moved towards this oxenium ion. This is your oxenium ion. So here the electron moves through this oxenium ion and there is a formation of a tetrahedral intermediate. So this tetrahedral intermediate is formed here. So in the next reaction, you will see the tetrahedral formation formed here is now reacted with the base. So here the acid-base reaction deprotonated the alcoholic oxygen. So here you will see this base will react with this H and it will take with it, and after that the H positive, the acid-base reaction need to be to make an OH leave. So here there should be a leave of this OH. This OH should be removed here. So here an acid-base reaction need to make an OH leave. It does not matter which one, so convert it into a good leaving group by protonation. So by the protonation, by this H positive when it is reacting with this OH, so there is a leaving of this OH group from here. Either this can be leaved from here, either this can be leaved from here. And here this H positive will react with this OH and there is a formation of this water molecule. You see here, this is a formation of this water molecule. So again, I am telling you the first 2 steps. So in the first 2 steps, you will see that this H positive, which is the acid catalyst, this acid catalyst is reacting with this O because O is having electrons present on it and this proton needs an electron. So this O will react to this H positive and there is a formation of this bond, that is your OH. After that, this become more electrophilic. This carbonyl will become more electrophilic. Then this alcohol will react. This alcohol will act as a nucleophile and it will react to this carbon atom. So there is a shifting of this bond from here to here. And there is a formation of this tetrahedral structure. So this tetrahedral structure is formed here. After that, this tetrahedral structure, this tetrahedral, this base will react with it. This base is reacting, B is having an electron, so it will withdraw the H from the proton from air. That is why here written the deprotonation, means the H positive is removing from this intermediate. So the deprotonation means the H positive is removing from this oxygen, that is your alcoholic oxygen, and you will see an oxygen's positive charge will remove from here because it is having now its lone pair. So here this H positive is withdrawn from this base. After that, this in the fourth reaction, you will see this product is formed. In the fourth reaction, an acid-base reaction, you will see this proton will withdraw electrons from this, will attach or bond to form a bond with this OH, and there is a leaving of this OH. We have to leave this, there should be a need to make an OH leave. So here this can be removed or this can be removed. Any OH group can be removed from here. So this H positive will attach to this OH, and there is a removal of this water molecule. You will see there is a formation of this water molecule. After the removal of the water molecule, you will see that this bond is withdrawn by this H2O, and there is a removal of this water molecule. After that, there is this bond, this lone pair will shift to this position, and there is a formation of this type of intermediate. So use the electron of an adjacent oxygen to help push out the living group, a neutral water molecule, and a neutral water molecule, and there is a formation of this intermediate. This is formed. So here, this this oxygen will withdraw electron from here, and it will be removed out from here. This water molecule is removed out from here. Then after that, there is a deprotonation of the oxygen ion, reveals the carbonyl in the ester product. So here now, this H also will be removed from here. This H will also remove from here. After this removal, there is a formation of the double bond. So the double bond is formed here. Now this H is removed from here, and there is a formation of this carbonyl carbon, this oxygen, a double bond. So in the sixth snap, there is a deprotonation of the oxygen ion to use the carbonyl in the ester product. So here this H will remove out from here. There will be a deprotonation. After that, there is a reveal of the carbonyl. Means there is a carbonyl that is present in the ester product now is revealed. This now you will see that this ester is formed here, plus hydronium ion is formed here. Next is your hydrolysis of your fatty acids. Now hydrolysis of the fatty acid, the reaction can be catalyzed by acid base or lipase, but it is also occur as an uncatalyzed reaction between fats and water dissolved in the fat phase at suitable temperatures and pressure. So here hydrolysis means in the presence of the water, there is a lysis of the fatty acid. So the reaction can be catalyzed. So this reaction which will be happening, that will be catalyzed by the acid or your base or the lipase. Lipase is an enzyme that is present in the fatty digestive system. So here the reaction that is happening, that is catalyzed by an acid, base or lipase, but it also occurs as an uncatalyzed reaction between fats and water. So it is also occur as uncatalyzed reaction. It is also called as uncatalyzed reaction between your fats and water, because there is a presence of water, and dissolved in the fat phase at suitable temperature and pressure. So this reaction, this hydrolysis, can be catalyzed by an acid or base or lipase, but it can also be occurred as uncatalyzed, means there is no need of this catalyst acid base, and there is a reaction, and then that uncatalyzed reaction will occur between your fats and water, that is dissolved. This fat and water is dissolved in the fat phase at a suitable temperature, and pressure. At temperature and pressure, this fat and water will dissolve in this fat phase. But first is your non-enzymatic ester hydrolysis and the soap making process. So here the soap making process will occur, and this reaction is non-enzymatic. Means here there is no need of the enzyme. So here there is no presence of the enzyme, and there the ester is hydrolyzed in the presence of water. The ester is hydrolyzed, and there is a soap making process also. So in aqueous solution, you will see that the esters are subject to hydrolysis to the corresponding carboxylic acids and alcohol components. So here, in aqueous solution, the esters are reacting are subjected to the hydrolysis process, and there is a formation of this carboxylic acid and alcohol. In the first reaction, in the reaction of the fatty acid, we have already seen that there is a formation of this ester. An ester is formed from this carboxylic acid and the water molecule, sorry, this alcohol in the presence of this acid catalyst. So here, this reaction is your reversible reaction. So now ester is converting it into these carboxylic acids and your alcohol in the presence of your water. So here hydrolysis is occurring. So this in an aqueous, yes, in an aqueous solution means there is the presence of the water. So in there is in the aqueous solution, this ester is subjected to your hydrolysis, and there is a formation of this carboxylic acid and your alcohol component. So the reaction can be catalyzed, this hydrolysis can be catalyzed in the presence of a ester catalyst, that is your acid, base or lipase, and but it also occur, but it can also be occurred in the presence of your uncatalyzed reaction that is happening between fats and your water and dissolve in a fat phase at suitable temperature and pressure. And the first is your hydrolysis of fatty acid. The first reaction is involved that is non-enzymatic ester hydrolysis. Means here there is no need of this enzyme and the soap making process, and there is a formation of the soap. So here in the ester, you will see the ester is hydrolyzed in the presence of the water or in the aqueous solution, and there is a formation of this carboxylic acid and alcohol, or you can say this is the reversible reaction of the esterification. Makes the mechanism of the base hydrolysis of esters. So here the this is happening in the presence of the base, and there is a hydrolysis of this ester. So here you will see from this water molecule this OH negative is reacting to this carbonyl carbon. So here the hydroxide nucleophile attacks at the electrophilic C of the ester C double bond O, breaking the pi bond and creating the tetrahedral intermediate. So here you will see this hydroxide ion is attacking, this is acting as a nucleophile and is attacking to this carbonyl carbon, and this carbonyl, when it will attack to this carbonyl carbon, then there is a shifting of the bond towards the oxygen atom. The oxygen will shift the electron from this carbon, so there is a presence of the positive charge on it. That is why this nucleophile OH negative will attack to the carbon atom, and there is a breakage broken. The bond between this oxygen and carbon will be broken, and will break, and this pi bond is break, and there is a formation of a tetrahedral intermediate. So you can see that there is a formation of the tetrahedral. The carbon is attached to the fourth side. So one side it is an oxygen atom, and the another side it is CH3, and the third side it is OH, that is the alcohol, and the fourth side it is methoxy, that is your ester OCH3. Now you will see, so in the second step you will see that this O will now with it is having a more electron pair present. Now the intermediate collapses, deforming the C double bond O, resulting in the loss of your living group, the alkoxide arrow leading to the carboxylic acid. So here you will see that the intermediate collapses. So here the intermediate now formed will be collapsed, and will collapse and deforming the C. Again, there is a, in the first step, we have seen that there is a breakage of this breakage of this pi bond between the C double bond O. But here again there is a reforming of this bond between this carbon and the oxygen. So, so here you will see there is a reforming of the C double bond O that results in the loss of the living group, the alkoxide. So here you will see this RO is lost by this living group, the alkoxide RO, and there is a formation of this carboxylic acid. And you will see here this bond that has been broken, that will be reformed, and you will see this bond, this negative charge is here because there is having a more lone pair, so more than two lone pair. So this now the third lone pair will be forming a bond between the carbon and the oxygen, and this oxygen will draw electron from here, it will remove out from here. So there is a formation of the carboxylic acid. So this is carboxylic acid is formed. This is removed from here. Now in the step third, you will see an acid and base reaction is happening here. A very rapid equilibrium where the alkoxide RO negative functions as a base deprotonating the carboxylic acid. The RCO2H, an acidic workup, would allow the carboxylic acid to be obtained from the reaction. So here the acid-base reaction, a very rapid equilibrium where the alkoxide, that is your RO negative, that has been removed from this intermediate, tetrahedral intermediate, as a base. Now it will act as a base and it will deprotonate the carboxylic acid. So here you will see that this RO that has been removed from this tetrahedral now now it will act as a base and it will deprotonate the hydrogen from this carboxylic acid. So here this RCOO2H, there is an acidic workup and that will allow the carboxylic acid to be obtained from this reaction. So this from here, this base will attack to this hydrogen atom. And if this base will attack to this hydrogen atom, there is a formation of this alcohol and this carboxylate ion is formed here. And this is a very fast reaction. As this is removed from here, and then this nucleophile will attack to this. Now it will act as a nucleophile, means it is acting as a base and it will remove this hydrogen from here and this bond will shift it to here. And there is a negative charge on this oxygen atom. Now that is your mechanism of the base catalyst. Base catalyst that is causing the hydrolysis of the esters. Now this is the mechanism of the acid catalyst that is causing the hydrolysis of the ester. So in the first step, you will see that this is your H positive, that is your acid catalyst. And an acid-base reaction, since we only have a weak nucleophile and a poor electrophile, we need to activate the ester. So protonation of the ester carbonyl make it more or electrophilic. So here we are having a weak electrophile, and in the an acid-base reaction, this is an acid-base reaction, and we we are having a weak nucleophile and a poor electrophile. So we have to activate this ester. The protonation of ester carbonyl carbon make it more electrophilic. So here, if this oxygen will be attacked by the proton, then the electrophile, that is a carbon, it will become more electrophilic. So the proton of the ester carbonyl make it more electrophilic. So this H positive, that is your acid catalyst, that will attack this oxygen, and there is a protonation of this ester, means there is the addition of the proton on this oxygen atom because it is having a more electron pair. So there, that is why the H positive will attack to this oxygen atom, and there is a formation of this bond, that is your OH bond is formed here. OH bond is formed here. Now in the step 2, you will see here a bond is formed here, OH, and after that the water O functions as a nucleophile attacking the electrophile C in the C double bond O, with the electrons moving towards the oxygen ion, creating the tetrahedral intermediate. So here this O functions. So this water O functions as the nucleophile, and the this in the water molecule, this O will function as a nucleophile, and it will attack to the electrophile, that is your carbon, and there is a shifting of this bond. Is the bond is shifted towards the oxygen atom, or you can say the breakage in the bond. So in the when the nucleophile is attacking the electrophile in the C-double-O, with the electron making towards, so these electrons are moving towards the oxygen ion, and there is a formation of this tetrahedral structure. So here you will see there is a formation of this tetrahedral structure, that is your this tetrahedral structure. When this H positive attack to this oxygen atom, because this oxygen is having a more electron pair, so this H will react to this. So there is a protonation on this compound. So the protonation of this compound makes this carbon more electrophilic. So this carbon will become more electrophilic. This carbon will become more electrophilic, and this now this electrophile, in this electrophile, this oxygen is acting a nucleophile. So this nucleophile will attack this carbon atom. Now this nucleophile will attack this carbon atom, and there is a nucleophile will attack this carbon atom, and this electron will shift towards oxygen ion, and there is an attack on this, and there is a formation of this tetrahedral structure. So here you will see there is a formation of this tetrahedral structure. Next, in the steps of third, now this tetrahedral structure is formed. Now this tetrahedral structure, an acid-base reaction that deprotonate the oxygen that came from the water molecule to neutralize the charge. Now again, now the water molecule, this water molecule which was added further in the reaction in the previous step. So here you will see that there will be a deprotonation, means from the water molecule, H will remove out from here. So this is known as your deprotonation. So when H will deprotonated from this oxygen, then from the water, then it will neutralize the charge on the oxygen atom. Now the oxygen atom charge has been neutralized. So in this step, you will see that this water molecule will attack to this hydrogen, and it will deprotonate from this oxygen, and there is a neutral charge on this oxygen atom. So this oxygen atom is a neutral charge. Now in the fourth reaction, you will see an acid-base reaction need to make the OCH3 leave, but need to convert it into a good leaving group first by protonation. Means here the protonation, the H positive ion that is reacting with this OCH3 and making it a good leaving group. So this OH3 has to become a good leaving group. It is need to convert it into a good leaving group. So it is attacked by this proton, and there is a protonation. There is a protonation on this oxygen atom, and there is a removal of now this. There is a formation of this bond. Now in the step fifth, you will see here when this this O is protonated. Now this use the electron of an adjacent oxygen to help push out the leaving group, a neutral methanol molecule. So here the electrons of this oxygen atom, they are pushed out, and there is a removal of this methanol molecule from here. Neutral methanol molecule will remove out from here. So you will see in this step there is a removal of this methanol group from here, and there is a formation of this product. This product is formed in. Now the product that is formed, an acid-base reaction, the deprotonation of the oxygen ion reveals the carbonyl C-double-O in the carboxylic acid product and regenerate the acid catalyst. So here there is a deprotonation. Again, the deprotonation of the oxygen ion means from the oxygen ion, this hydrogen will remove from here, or you can say the H positive will be deprotonated, means removed out from here, and there bond shifted and the oxygen become neutral. So this reveals the carbonyl COO in the carboxylic acid group product and regenerate the acid catalyst. So here you will see this is your H2O that will take this oxygen, that the hydrogen and the bond that will shift to here oxygen, and there is a formation of this carbonyl compound. You see double bond. And again, there is a formation of the H3O positive, that is a hydrogen ion. So here you will see there is a formation of this carboxylic acid as well as this alcohol molecule is formed from this acid catalyst, and from the base catalyst also the same products are formed, that is a carboxylate ion and the methyl alcohol is formed. But the difference is that there we have used the base that is your OH negative, and here we have that reaction was catalyzed by a base, and here this is catalyzed by an acid, that is your H positive. So these are the two reactions that are showing the catalyst. In the presence of the catalyst, this hydrolysis reaction of the ester is occurring. Next is the hydrogenation of oil. So what is the hydrogenation of oil? So the saturated fats are solid at room temperature due to their molecular shape. The term saturated is in reference to an sp3 carbon chain that has its remaining sp3 orbital bonded with hydrogen atom. Thus the term saturated is saturated with hydrogen. So here the saturated fats, I've already told you that the saturated fats are solid at room temperature, and there is a presence of the saturated ring on that fat. Means there is a presence of the saturated hydrocarbons in this fat. There is a presence of the single bond between the structure of this fat, and that is why they are solid at room temperature due to their molecular shape. Because of their molecular shape, the presence of the molecular shape, they are fats. These saturated fats are solid at your room temperature. The term saturated is in reference to an sp3 carbon chain that has its remaining sp3 orbital bonded with the hydrogen atom. So here, the term that we have used here, that is your saturated, is referring that the sp3 carbon chain, because the chain that is your sp3 carbon chain, all the carbons that are present in the chain of this fat are all sp3 carbons. So the sp3 carbons are then bonded. All the sp3 carbon atoms are bonded. Carbon chain is bonded with the hydrogen atom. These sp3 orbitals are bonding with the hydrogen atom. Thus the term saturated. That is why the term saturated is used here. So they are saturated with your hydrogen atom. So all the carbon chain that are having the sp3 orbital, they are bonded to the hydrogen atom. That is why the term saturated is used here. And this saturated means that it's saturated with hydrogen. This is saturated with your hydrogen. So the saturated fats have a chain-like structure. So the saturated fats have a chain-like structure which allow them to stack very well, forming a solid at room temperature. These saturated fats are having a chain of this carbon chain, and this is having a structure that is allow them to form a stack very well. And these stack is forming a solid, and this solid is forming at a room temperature. So the unsaturated fats are not linear due to double bonded carbon, which result in a different molecular shape because the sp2 carbons are trigonal planar, not tetrahedral, as the carbons are in saturated fat. So here you will see the unsaturated fats are not linear. They are not linear because they are containing the double bond in them. Unsaturated means there is the presence of the double bond. So here there is a result in a different molecular shape. So the shape of this unsaturated fats are different, and because there is a presence of this sp2 because there is a presence of this sp2 carbon, which is your trigonal. Sp2 carbons are always present in the trigonal planar, and the sp3 carbon are in tetrahedral. So these sp3 carbons are not in the tetrahedral structure. So these carbons are in the saturated fats. This change in structure will cause the fat molecule to not stick very well, resulting in fats that are liquid and at room temperature. So the change in the structure of this unsaturated, this fat molecules in this saturated fats, they are not forming a stack-like structure, and this will result in the formation of liquid, that these fats are liquid at your room temperature. So butter is mostly saturated fat. That's why it's solid at room temperature. So your butter is such an example of this saturated fat, and that is why it stacks very well, and they are solid at your room temperature. Olive oil is liquid at room temperature, thus it is an unsaturated fat. An unsaturated fat can be made into a saturated fat by a hydrogenation process. So this olive oil, which is liquid at room temperature, it is an unsaturated fat, and this unsaturated fat can be made into a saturated fat by a process, that is your hydrogenation process. So from this hydrogenation process, we can convert the unsaturated fat into your or saturated fat. During the hydrogenation process in the production of trans fat, the trans fats are a result of site reaction with the catalyst of the hydrogenation process. So in the production of your trans fat, and the trans fats are a result, these are formed from the side due to the side chain that with the catalyst of the hydrogenation process, and it is a result of an unsaturated fat, which is normally found as a cis isomer convert to a trans isomer of the unsaturated fat. And this trans fat is a result. This is formed from the unsaturated fat that is present in the cis isomer form, but then converted into the trans isomer form of the unsaturated fat. And the isomers are molecules that have the same molecular formula but are bonded together differently. So these isomers, cis and trans, these are both the isomers, and these isomers have the same molecular formula. These isomers is having the same molecular formula, but the bonding between them are different. Focusing on the sp2 double bonded carbon, a cis isomers has a hydrogen on the same side. So the cis isomers that is having a sp2 hybridized carbon, sp2 double bond carbon, these are having a cis isomers. On this cis isomers, the hydrogen are present on the same side of the structure. Due to the added energy from the hydrogenated process, the activation energy is reached to convert the cis isomer of the unsaturated fat to a trans isomers of the unsaturated fat. The effect is putting one of the hydrogen on the opposite side of one of the carbon. So in the trans isomers, the hydrogen are present on the different side of the opposite side of the different opposite side of the carbons, and this result in trans configuration of the double bonded carbon. So the human body does not recognize trans fat. So the human body does not recognize this trans fat. So although the trans fatty acids are chemically mono unsaturated or polyunsaturated, they are considered so different from the cis mono unsaturated or polyunsaturated fatty acids that they cannot be legally designed as unsaturated for purpose of labeling. So here, these trans fatty acids, they are your monosaturated and polysaturated, and they are considered different from this cis monosaturated or polysaccharide unsaturated fatty acid. So they cannot be legally designed that for the labeling purpose, for the and legally designed as your unsaturated for purpose of labeling. So most of this trans fatty acids produced by the partial hydrogenation process are now classified in the same category as saturated fats. So these trans fatty acids, which are still chemically still unsaturated, these are produced by the partial hydrogenation. These are produced by the partial hydrogenation process, and these are classified as the same category as your saturated fats. So the major negative is that trans fat tend to raise bad LDL cholesterol and lower good HDL cholesterol. So here the negative effect of this trans fat is that they are raising the bad LDL cholesterol and uh, and lowers and it has lowering the HDL, good HDL cholesterol, although not as much as saturated fat. Trans fats are found in margarine, baked goods such as donuts and Danish pastries, deep fried foods like fried chicken, French fried potatoes, snack chips, imitation cheese, and confectionery fat. These fats are trans fats which are raising the bad LDL cholesterol and lowering the good HDL cholesterol. They are present, they are found in margarine, baked good, and baked goods such as your donut and Danish pastries, deep fried foods like your fried chicken and your French fried potatoes, snack chips, and the imitation cheese and confectionery fats. Now, the hydrogenation definition. The hydrogenation is a chemical formula, chemical process that where the hydrogen is reacting with the organic compound, and it refers to the saturation of unsaturated liquid oil with hydrogen atom. What means here the unsaturated liquid is converting into the saturated. So molecules in unsaturated fatty acids are banned and not allowing them to pack close together closely. These in this unsaturated fatty acid, they are packed, not packed closely. The limits the intermolecular attraction force make it their melting point lower, which means that they are liquid at room temperature. These are making the intermolecular attractive force and making them their melting point lower. That they need these liquids are they are liquids at room temperature. The hydrogenation process removing those kinks, bands, and make the fatty acids straight. So these bands have been removed by this hydrogenation process, and this makes the fatty acids straight, and either by making fully saturated or altering them to trans fatty acids. So both saturated and trans fatty acid chains are straight, therefore they can stack up closely together, increasing their melting point. So this after that they are converted to the saturated and trans fatty acid chain, become straight, and now they can stack closely together, so they can be packed together closely, and this makes that melting point increase or high. The main purpose of hydrogenation oil to solid or fatty acids or semi-solid fats are that they are the chief substituents of saturated fats that are obtained from animal origin, such as lard or butter. And hydrogenated oils are more stable than your unsaturated oil. And this process of hydrogenation, transforming fatty acid to oxidative rancidity, especially in high temperature during cooking, and the hydrogenated oils are also more stable than your saturated product, that is your such as your butter. Although butter is considered as a saturated fat food, and it contains some short chain fatty acid and unsaturated fat, and both of which are more prone to rancidity than long chain saturated fatty acids that are present in the hydrogenated product. Next is your full hydrogenation. Full hydrogenation means full saturation. The full hydrogenation process that saturates all carbon atoms with the maximum possible number of hydrogen atoms, and this makes the oil fully saturated. Means there is no more hydrogen bond that can be attached, or also no trans fatty acid exists. So the process of full saturation transforms unsaturated into the fully saturated fatty acid. So all the kinks and bands are being removed from the structure and they are made straight. So the shape of the chain becomes straight. Therefore, they can be stacked up together closely and they can be packed closely also. So this form a straight or solid fat in room temperature. Next is what is partial hydrogenation or partial saturation. The partial hydrogenation is the incomplete process. This means that there is a hydrogen process stopped before there is a complete transforming of into the full saturation of carbon with hydrogen atom. As a result, there are some of the double bond present, and some of the double bonds are having a cis configuration, and some have the damage in the process, so forming a trans configuration where one of the hydrogen of the carbon atom has been removed and another placed on the opposite side of the chain. The purpose of partial hydrogenation of oil is to make the property optimal for food preparation, and the partial hydrogenation is resulting in a product that is more suitable for culinary purposes than fully hydrogenated product. Now, what are the oils only? Why are oils are only partially hydrogenated? The partially hydrogenated oil can give a wide range of consistency of the finished fat product, and fully hydrogenated oil would make the oil hard at room temperature and not as versatile in food preparation. This increases the stability and the shelf life of the fat and processed food. And these are extremely cost efficient and preferred for their usability in the most commercial baked food. So here you will see this is your unsaturated, and these from here, these are oxidized and acid catalyzed. So there is a formation of this. Now here you will see that the proposed mechanistic pathway for the formation of oligomers or polymeric products. Next is the drying oil. So the drying oil is the oil that hardened to a tough solid film after a period of exposure to oil. This oil hardens through a chemical reaction in which the component cross-links and polymerizes and by the action of your oxygen. So the drying and the semi-drying oils are the vegetable oils that are making it color, namely linseed oil, poppy, and the sunflower. So the different method of processing oil produces products with different drying rates, consistency, and color. So the semi-drying oil is oil which is partially hardened when it is exposed for oil, air when it is exposed to air. This is and proposed to an drying oil which hardens completely, or a non-drying oil that does not harden at all. So oils having an iodine number of 115 to 130 that are considered semi-drying. Yes, these are the non-drying oils is oil which does not harden when it is exposed to oil, and this is opposed to drying oil which hardens completely, or semi-drying which partially hardens. So these oils are having a iodine number that is less than your 150 that are considered non-drying. So this is the proposed mechanism pathway for the formation of your oligomers or your polymeric products. Now the rendification. So the rendicity is the complete or incomplete oxidation or hydrolysis of fat or oils when they are exposed to the oil, air, light, moisture, and bacterial action. This is resulting in an unpleasant taste and odor. Especially it is a hydrolysis or auto-oxidation of fat into short-chain aldehydes or ketones, which are objectionable in taste and odor. So the pathway for rendification is this: the hydrolytic. The hydrolytic rendification, rendicity refers to the order that develops when triglycerides are hydrolyzed and the free fatty acids are released. So in this hydrolytic, the free fatty acids are released, and these triglycerides that are present in the fats that are hydrolyzed. This reaction of liquid with water may require a catalyst. So from in this reaction, there is a requirement of the catalyst leading to the formation of the free fatty acid and glycerols. So now this is the oxidative. The oxidative resistance is associated with the degradation of oxygen in the air. So the double bond of an unsaturated fatty acid can be cleaved by the free radical reaction involving molecular oxygen. So the antioxidant that are used as a preservative in fat-containing food that delay the onset or slow the development of rendicity due to oxidation. So these antioxidants will preserve the delay or the slow development of rendicity due to oxidant. So the natural antioxidants are your ascorbic acid, your tocopherol, that is the vitamin E. Synthetic antioxidant includes your butylated hydroxyanisole, that is your BHA, butylated hydroxytoluene, tetra-butyl hydroxyquinone, or propyl gallate and ethoxyquinone. So these are the structure of your BHA, BHT, PBHQ, or polygallate. So the microbial rendicity refers to the process in which microorganisms such as your bacteria or mold uses their enzymes that is your lipase that break down your fats, and there is a sterilization can reduce this process, because in the sterilization there is a microorganism can be removed from it. So here these are the antioxidant that has been used for the preservation or to stop or to slow down the process of rendicity, which is happening due to the oxidation. This is the structure of your vitamin C. This is the structure of your vitamin E, that is your tocopherol. This is ascorbic acid. This is a toxicoid. Next is the question. Select the incorrect statement from the following option. First is your oils are saturated. Triglycerides oils have lower melting points. Oils are liquid at room temperature. Examples of oils are glycerin, triolate, coconut oil, or olive oil. That is the oils of unsaturated triglycerides. Saturated fat. Which of the following is an example of fat? That is a vegetable. Select the incorrect statement from the following. That is the oils are saturated triglyceride. Hydrogenation is a conversion of unsaturated acid groups into the saturated one of the catalyst, that is the nickel. Oil and fats are good conductor of heat and electricity. False. Which of the following act as a catalyst in digestive tract of human body? That is your lipase. All of the following have 18 carbon atoms except palmitic acid. Vegetable ghee is manufactured by your hydrogenation. Hydrogenolysis is a reaction which leads to a reaction of product of alcohol. Glycerol is a precursor of all except bilirubin. So these are the references from where you can study this topic. And thank you so much for today's lecture.